In this lesson, we're going to read some MCU startup code that runs when power is applied to the MCU or it is reset. We'll start by doing some updates to the device configuration in the IDE to get us to the final configuration for the course project. Then we'll look at three main files that contain initialization code. We start with the initial startup code. The same file contains the interrupt vector table, including the reset vector. And this is the one file in assembly language. Now, to fully understand the code in this file does require knowledge of assembler. I realize almost none of you will have that. So what I hope to do is describe what the code is doing to give you the general idea, even if you don't understand all the details. It isn't really that much code we will look at. Now, although I started my career writing only assembly code, in the last 35 years I only rarely looked at assembly. And the few times I did, it was often startup code just like this. So following this, there is another file that contains common system initialization functions for the MCU we are using. By common, I mean that this code would be the same for all MCUs of the type we are using. It does not depend on the peripherals we have chosen in the IDE. Also, it doesn't depend on whether you're using LL or HEL device libraries. In fact, it's using the SEMSYS API, which is almost below LL and HEL. And then we end with the main.c file. And this is generated code. It performs initialization based on our chosen hardware configuration, such as peripherals. It also depends on the fact that we are using the LL device library rather than HEL. I should say that main.c is not the only generated code in the project, but it is a major part. Now, below in this box, I list the locations of the files we will be reading relative to the project folder. And by the way this IDE works, it copies all the needed device library code files to the project folder when you generate code. So all the code for the project is in the project folder. Of course, the actual image that you burn into the flash also contains object code taken from the standard C libraries that we discussed in a previous lesson. Here's a list of things we need to do in the device configuration tool in the IDE. We will add support for UART6. UART6 will be used to talk to the GPS module. I happen to know that the baud rate of that module is 9600, and we'll set that. Then we'll configure all devices to use the LL libraries rather than the HEL libraries. And finally, we will remove the hello world code that we had put in main.c. That was just test code to verify the console. And that code depends on HEL, which we are removing. Here we are in the device configuration view of the IDE. So the first thing I want to do is add the UART6. So we'll select that. Open the parameters window, set the mode to asynchronous. It has picked these two pins, which are the ones I wanted it to pick because I already have the wiring set up. Now we go to the parameters and we set the baud rate to 9600. While I'm here, I'll just mention it has an option to enable the interrupt, and I think if we select that, it will generate code to do that, but I'm going to handle that in the module, so we don't need that. Then we go to the project manager, and we want to make everything LL. And that's done. Now I'm going to remove the hello world code from main.c. It wants to go back to C++, and that's fine. So I'm already in the loop here. These two lines here are the hello world lines, so I'm going to remove those. And then you may remember I put in a header file, include statement. So now I think we're ready to go. I will build the code or generate the code. It wants me to it wants me to save the files. And I'm going to pause the recording while this is going on. Okay, that didn't take too long. Now, just as a check, I'm going to build the code. It should build. Looks like it's rebuilding every file. And it's linking, and it works. So great. So we regenerated the code. Now it's time to look at some of the startup code. Here I am in VS Code where I've opened my project directory called MCU-class-1. I'm using VS Code because I prefer it over the IDE editor. And I've opened up the assembly language startup file, which is under core startup. And here it is. Now, assembly language can be confusing because of all the syntax. A key thing to remember is that many of the lines in an assembler file don't generate machine code instructions at all. They are called directives, and they normally start with a dot, like, for instance, these lines here. And they are giving instructions to the assembler. Anyhow, the first thing I want to look at is the interrupt vector table, and I will go to around line 123. So this is the beginning of that table, but I first want to look at this dot section directive here. We're telling the assembler that the following code or data in this file should go into the section named .isr underscore vector. You might remember this section name from the lesson on building code. This section gets mapped to the start of Flash. Now back to the table, notice all these .word directives. They are telling the assembler to reserve a word of memory, which will be 4 bytes on this machine, and to set that word equal to the value of the symbol. Now, most of these values are pointers to code in this file, and we'll look at those in a minute. This one is different. This symbol comes from the linker, and this is the initial stack pointer. So what happens with this MCU, when it powers up, it takes the first word from the interrupt vector table and loads it into its stack pointer. It takes the next word and loads it into the program counter, and then it starts executing instructions, which will be at this wherever this symbol resides. So let's go to the reset handler code, which I know is higher in the file, and here it is. So before I start looking at the actual code, again, there is a dot section directive, and it's telling the assembler that the following code or data goes into this dot text dot reset handler section. And these sections are the ones we discussed in the lesson on building code. So now let's look at the actual reset handler function. And this first line is now generating actual code. LDR stands for load register, loads a value into a register. SP is the name of the register, that's the stack pointer, which is a key register in a CPU. It's used for interrupts. It's used when you call functions. And this is loading the stack pointer with the value of this variable called _e_stack. Now you might say, wait a minute, didn't the MCU already load that value out of the interrupt vector table? I would say, yes, I think it did. You would then ask, why is this instruction here? And I would have to say, I am not sure. It seems redundant. Maybe there's a reason for it being there, but it doesn't do any harm, so let's move on. So the next thing we do here is prepare to run C code. And there's a few things you have to do before we actually start the main function. As you know, you can have global and static variables that have non-zero initial values. So how do those variables get set with those initial values? Someone has to do it, and it's this code that we're going to look at right now. What these three instructions are doing, again, they're loading registers, except in this case, they're loading these general purpose registers that are sort of like, temporary variables. It's loading the first one with the value of the symbol underscore S data, the next one with underscore E data, and the next one with underscore SI data. These first two are the beginning, the start, and the end of the .data segment. That's in RAM. This third one is the start of the initial data for the .data variables, the values. And this is in Flash, so it is persistently stored. The next register, R3, since I've looked at this code, I know what it's going to do. That is like a index and an offset. And ignore this instruction for the minute. So basically what we got here is a loop. And here is the body of the loop. And basically the loop is copying initial values from Flash into the .data segment and thereby initializing those variables. And what these three instructions do, this first one, it's a load register into R4. Now in this case, it's using the pointer into Flash and this R3, which is an offset, and getting a value. And then the next register, or the next instruction, is storing that value into RAM. They then add 4 to the offset, so we're ready to do the next word. And then these instructions at the end are deciding whether or not all the copying is done. And it's comparing some registers. And now if we go back to this instruction, the B stands for branch, and then this is the symbol of where you're going to branch to, which is down here. So this is often how loops are done in assembly. You actually jump to the end of the loop where it does the check. And by the way, if in this code that's doing the check, if it's not done, that's what this branch here is. This is a conditional branch. If it's not complete, it goes to the top of the loop again. So that takes care of the variables in the .data section. So now we have to do the BSS section. And BSS section contains static and global variables that have initial values of 0. So it's a little bit easier. So again, we load some registers with the beginning and ending of that section. I just noticed it uses the word segment in this comment, and there is a subtle difference between section and segment that doesn't mean as much for embedded. I'm just going to let that go. I think it's something you don't need to worry about. Anyhow, we're loading the beginning and ending addresses, and then here is and we're branching here to the end of the loop. Here is the actual body of the loop, and what it is doing is storing a register to a value in RAM. And what's the value of that register is R3. That's set to 0 and it's never changed. So we are zeroing out the BSS section. So once that's complete, we're getting close to the end. BL, system init, this is branch with link. And this is how you do a subroutine or function call in ARM assembly. What that's saying is branch to this symbol, but before you do, save the address of the next instruction into the link register. That's another special register. So system init, that code will run, and when it's complete, it will jump to the value in the link register, and we'll end up here. When we end up here, we're calling another function, libc init array. This is more preparation for C code to run. For those of you familiar with C++, in C++ you have this concept of static objects, and their constructors run before main begins. So if this were C++, I believe that's where those constructors would run. And then the final thing we do, or we believe it's the final thing, is we call the main function, branch with link to main. Now, normally you wouldn't expect main to return in this embedded system. It runs forever. What if it did return? Well, what this code here is doing, it tries to return to whoever called it. This is branching to the address that's contained in the link register. Well, I don't know what will happen in this case. This function was called via hardware, right? When the MCU powered up. What it does in that case, I'm not certain, but you really shouldn't return from main. Now let's look at some more of those entries in the interrupt table. So these vectors at the top are internal interrupts generated by the CPU, typically when something goes wrong that it detects. One possibility that would relate to your code would be a bad pointer. Sometimes causes the CPU to have an exception. The bulk of these interrupts, though, are for peripherals. And so as we go through these, you'll see here are ones for timers. Here's some for I2C, I2C interfaces. Here's SPI. And here's USART. And so I want to look at the USART one as an example. So that vector had a value, here it is, USART1. And what this line of assembler here tells the assembler that to mark USART1 IRQ handler as a weak symbol. And then this directive sets the value of this symbol, the USART IRQ handler, with default handler. And you'll notice that all of these interrupt vectors are all set to default handler. So, of course, the question is, what does the default handler do? And we'll see that in just a minute. Here's a section putting this little bit of code into that text.text.default handler. And then here is the actual entry. Here is a label in the code. And what does the code do? It just branches to itself. So if one of these interrupts go off and the default handler handles it, your system will go into a tight loop and it will stop doing everything. You'll look at it and you'll say, what's going on? If you have a debugger connected to it, you could break into the debugger and you'll see that it's in this loop. And I am not sure, I can't remember how much information the debugger will give you as far as how it got there, but you'll know what the problem is. And so at that point, it's either your code did something bad that caused the CPU to generate an interrupt, or you have some peripheral that you might be using that generated an interrupt and you didn't set up the interrupt handler. So that's a key point. To set up the interrupt handler, you use one of those symbols that we just looked at that are defined as weak and create your own function with that name, and then that function will be called when the interrupt goes off. Now, it would be nice if there was a way in here that you could sort of put your own handler. And I don't see a way of doing that. Maybe there is. Obviously, you could modify this code if you had to, and so that you could have your own handling of unexpected interrupts. But the first thing you need to do is just make sure you define um, interrupts for all of the hardware that you're using. Here we are in the file containing the function system_init that we saw being called from reset handler. This function is defined in the SEMSYS API, and it's located in the project under core source. So let's go to that function, which happens to be on line 168. So here it is, and the function is not very long. It just goes down to here. The other thing you'll notice on this function is there are really 3 lines of code. Um, Here's 1, 2, and 3. But they all have these hash shifts around them. And if you aren't fluent in C, this is something you'll need to learn about. Um, these are being used to conditionally include or not include code into the build. And basically, you can think of underscore FPU present as a flag that would be set true or false based on the type of CPU. Um, Here's another one called data in external SRAM, which would be dependent on whether we have external data, and I know we don't on this Nucleo board. And then this one here is if you have a user vector table set up. So let me just go through these one at a time. If there's an FPU stands for floating point unit, and if it's present, some bits get set into a system register. I'm not sure what the purpose of that is. If we have external SRAM, which we don't, there's system init external mem control probably. That shouldn't be called in the case of the board I have. And then finally, this vector table address, I'm not sure exactly what's going on here. With some CPUs, you can take a copy of the interrupt vector table that's in flash and copy it to RAM, and then tell the CPU to start using the version that's in RAM. And the reason you would do that is it would be faster. That may or may not be what's going on here. Now we are in the file main.c, which contains the function main. You might remember that the last thing that the reset handler did was call this function. I'm not going to go through this code in great detail because it is mainly hardware initialization, which is not the focus of this course. But we can look at it and see how the initialization code is organized. Now keep in mind this is generated code. So let's go down to the function main, and here it is. And let's just start scanning through. Well, the first thing it does is enable some clocks, and notice these functions begin with LL. So that's the low-level, so-called low-level driver library. It's then setting up something on the interrupt controller, which is NVIC, and I believe that this function is coming out of the SIMSYS library. It's then calling system clock config. This function is generated code, which I happen to know immediately follows main. And there it is. And you'll see a lot of LL stuff. Now you might ask, wait a minute, the CPU is already running. How can we be setting up clocks? Well, it's a good question. The CPU comes up and it comes up in a way that will at least run. It might not run optimally, but it runs good enough to get you to this function so that you can then tweak the clocks and make everything exactly what you want. Things like peripheral clocks don't need, the CPU is not so dependent upon those. You do have to be careful though, if you get into this, about the order that things are done. So let's go back to where we were. Now we go through these, we call these three functions that are handling the peripherals that we have configured. So first let's go to GPIO init, and you will see that it is calling a bunch of LL functions. And there's one in particular I'd like to show you. This LL GPIO init is one of the higher level functions. It's not just setting a single register, it's doing a little bit more. And so what's happening here is there is a data structure where you're filling in all of the fields, the pin, the mode, the speed, and so forth. And then you pass that to this, to the LLGPIO init, telling it what port and then the details. So let's go back to where we were. And next we have a UART, and we'll go to that one. Again, we see a lot of, well, let me highlight the function name so you can see it. We see a lot of LL functions. Here we are configuring the GPIO for the UART, including doing the pin mapping. And then finally, we have to initialize the UART. And once again, it's filling in fields in a data structure, and then it calls this init function that does sets a number of registers with this data. So that's it for the UART. Try to go back. And then we do another UART, which is almost identical code, but for a different UART number. And then we get to an empty while loop. The generated code has done everything it can do. It's now time for the user code to take over. And in a future lesson, we'll be putting some code in here. So that's it for looking at code. So we took a quick tour of the startup code, and we found it all starts with the reset vector out of the interrupt vector table. Then we initialize memory to prepare to run C code. By the way, this was done in assembly code, but I believe it is sometimes done in C code. You just have to be very careful. Then we do hardware initialization via common and generated code. The generated initialization code seemed okay, but we should study it in detail to make sure it is doing exactly what we need. And by the way, this generated code can provide a good starting point if you want to take over from the IDE. So that's the end of the lesson. Thanks again for watching.